Good morning, everyone. So welcome to the morning session of the day 3 of the workshop. So today, so in the morning session, so the topic is about elastic properties and spectroscopy. So we have 6 speakers, and then each talk will be 30 minutes. So yeah, if you have any questions, about so the talk, please raise your hand or type it in the chat. And then our first speaker is Professor Zhu Mao from University of Science and Technology of China. And her talk is about perspective for Brillouin scattering in earth sciences.
So I would say, good morning, everyone. Actually, it has been 11 p.m. in China now. Okay, it's my great pleasure to have this opportunity to talk about the Brillouin scattering. That this is a technique that I have been used for years, try to study the elasticity of minerals in the earth science. Okay, so when we're talking about the elasticity, we think elasticity, of course, is a fundamental property of materials. Elasticity is very important for earth science. That is because when we're talking about the composition of the earth, we mainly rely the information from the seismology. Of course, from the seismology, we see that they provide the sound velocity of different layers of the earth. So if we know that the elasticity of different minerals, we know the density of different minerals at different depths, we can build up our own velocity profile and compare our modeled velocity profile with seismic images. Of course, this can tell us the composition variation at the different depths. Okay, so that's the reason we think elasticity is very important. And especially in recent years, seismologists, they actually identify lot of velocity anomalies at various depths or various locations of the Earth. Here, I just show you 2 examples. One is a low velocity zone that is present above the 14-kilometer discontinuity. The other one, actually, they also observe about 2 to 7% reduction in shear wave at the at the bottom of the transition zone. So this tells us if we want to decipher the origin of those velocity anomalies, we have to have a better knowledge about the composition variation, the influence of composition variation on the elasticity or the sound velocity of different minerals. So that's the reason. So we have to do some work or the experimental measurements, try to decipher those formation mechanisms of those velocity anomalies. So here I show 3 examples that all of those are typical experimental techniques that we have been used for years, try to determine the elasticity of minerals in the Earth's deep interior. For example, the first one is ultrasonic measurements. This one combined with the large volume press that we can see that we also can use at GSA cars. The second one, this is a photo from the UT Austin that is an impulsive stimulated light spectroscopy. And this is also a very important technique that we can use to determine the elasticity. The third one actually is what I try to focus today is about the Brillouin scattering. This is also a widely used technique. People have been used for a few decades to determine the elasticity of minerals. The beauty of the Brillouin scattering is that we can use it to determine the single crystal elasticity. So once we have the single crystal elasticity, we can combine it with the deformation experiments. And then this can tell us the anisotropy of minerals in the Earth's mantle. We can model the mantle flow. We can get the knowledge about the deformation history of the Earth's mantle. So that is the beauty of the Brillouin scattering, that we can have the single crystal elasticity. Here, I just go back a little bit in history that people use this technique to determine the single crystal elasticity of mantle minerals. So this is the work that has been published in Nature in 1995 by Tanzavi et al. So they use this technique to determine the single crystal elasticity of olivine at high pressures. And the results of this work actually have been applied to model the velocity jump of the 14-kilometer discontinuity. And people use this to estimate the volume percentage of olivine in Earth's upper mantle. Now, the second example actually is published in EPSL by Murakami et al. They determine the sound velocity of bridge light and the magnesium silicate post-perovskite. So you can see that they go over megabar pressures. So those work are very difficult and very important. They use their experimental results, try to understand the composition of the Earth's lower mantle. So my most recent work, actually, our group, we try to use Brillouin scattering, try to obtain the combining factor pressure and the temperature on the elasticity of mantle minerals. So when we look at most of the previous work actually were performed at either high pressure at 300 Kelvin or high temperature but 1 bar. That means when we try to use those experimental results to model the sound velocity of mantle minerals, we have to extrapolate these high pressure or high temperature results. So that's the reason we think that if we want to understand what is going on in our Earth, we have to get the knowledge about the combining factor pressure and the temperature on the elasticity. In this case, we can significantly limit our extrapolation, when we try to model the velocity profile of the Earth's mantle. So we think that actually the BMDJC cars is really very nice place that we can perform such kind of experiments. So you see that BMDJC cars they combine the Brillouin scattering with Raman with XRD. So when we are doing the Brillouin scattering experiments, we can simultaneously obtain the density information. So that means when we combine Brillouin scattering and X-ray diffraction, our experiments actually do not rely on any pressure calibrants or pressure scale. So we think those actually very user-friendly and very important facility that I actually have been using since 2008. I'll give you two examples about our work that we use the Brillouin scattering and X-ray diffraction at JC cars. This work actually has been published in 2012. This is our earliest work that we use this facility to investigate or to determine the single crystal elasticity of this iron-bearing hydrous ringwoodite. So although at that time, we only can reach 673 Kelvin, this temperature is really low. So this is our first simultaneous high PT experimental work. So anyway, using this facility, in this work, we determine the combining factor pressure and the temperature on the single crystal elasticity of hydrous ringwoodite. So from this work, you can see that we have the 300 K measurements, and then we get over maximum velocity maximum temperature velocity measurements, we get 673 Kelvin. And of course, we have to extrapolate our experimental results. If we want to model the sound velocity of hydrous ringwoodite at mantle conditions, we extrapolate it to mantle geotherm. So once we know the sound velocity of hydrous ringwoodite, we get the depth variation of the 660 kilometer discontinuity, and then we try to estimate what is the water content at the bottom of the transition zone. So from this work, I just quickly go over this work, So from this work, we see that actually at most places of the bottom transition zone, the water content is very low, it's less than 0.1%. So this is the first one and first example that I want to share with you that we use this facility to try to study the mantle composition. So the second example that I want to give you actually is our most recent work that we published in JRL this year. So this work, we actually focused on the velocity anomaly. So that is at the bottom of the transition zone, that is 570 to 660 kilometer depths. People actually have observed 2 to 7% reduction in the shear width. So some people argue that maybe this velocity anomaly is from the presence of water, and some people argue that maybe this velocity anomaly is present. This is caused by the subducted oceanic crust. So we don't know what's the formation mechanism. So in this case, okay, in this work, what we are doing here is we try to measure the elasticity of garnet. Garnet is the most important component of the subducted oceanic crust, but the composition of the garnet actually is very complex. You see that we can have pyrope, that is magnesium, we can have armandine, that is iron and a member, and we can have grosser, that is a calcium and a member, and we can have the meteorite. So the pyrope, grosser, armandine, and meteorite form a very complex solid solution. And especially from the petrological observation in most recent year that we see that the ferric iron concentration, there is a great increase in the ferric iron concentration with depth. So in the transitional that we can see the Fe3 plus content actually is pretty high. And this is another extreme case on the right that is published in Science Advance 2017 by Xu et al. So you can see that, I'm sorry, okay, I try to make a mark here. So we can see that, so this sample actually, they get this meteoritic garnet. The ferric iron content extremely high, and this meteoritic garnet actually is calcium depleted. So that means in our Earth, maybe the composition of the meteoritic garnet has a wide distribution in the composition. So maybe somewhere for the meteoritic garnet is calcium depleted, but Fe3 plus enriched, maybe in somewhere. So the meteoritic garnet has a completely different composition. That means maybe there is a lateral variation in composition of the meteoritic garnet. So that's the reason in this work, what we try to understand is what is the composition variation, how the composition variation can influence the elasticity of the garnet. And then we try to use this to understand the variation of the composition in garnet, how it can influence the sound velocity of the subducted oceanic crust. So that is what we try to do. Okay, so the first one that I show you here is one work that has been published in EPSL a few years ago by Liu et al. They firstly measure the single crystal elasticity of this pyrope. Okay, this work, they went to 1750 Kelvin and over 20 GPa. So in our work, so you can see our progress, okay, for this grosser sample, that is a ferric iron bearing sample, we already go from 673 Kelvin in 2012. Nowadays, we already can move to over 1000 Kelvin, that are about 20 GPa. So we actually made a progress when we try to perform such kind of simultaneously high pressure and high temperature experiments using the Brillouin scattering at BMDGC cars. So from this work, anyway, we determined the single crystal elasticity of this specific grosser up to 1000 Kelvin and 20 GPa. So using this single crystal elasticity and previous experimental work, you can see there are a huge amount of previous experimental results along the pyrope armandine solution and join and the pyrope meteorite join and this grosser and androlite join. Anyway, we combine them and we get those trends, and then we model the sound velocity of the subducted oceanic crust and also a hydrous mantle. So this figure actually is a little bit complex on the left. So on the left, so on the top, the panel A and the panel B, actually our modeling results, we try to understand the influence of water on the sound velocity of the bottom transition zone. So we can see here, okay, I'm sorry. So we can see here, the black line here. So the black line here actually represent the sound velocity of the dry paralytic mantle. So we can clearly see the 14 kilometer discontinuity and the 520 kilometer discontinuity from our meteorological modeling. So then we try to add water inside. So here we consider, okay, the influence of water on the velocity profile of the Earth's mantle in terms of the influence of the Audubon polymorphs, because nowadays the effect of water on the elasticity of Audubon polymorphs are much better experimentally constrained than other mantle minerals. So we can see here, okay, the purple line and the yellow line here, okay, they are the same water-bearing model, just the only difference is the water incorporation mechanism in ringwoodite actually is different. So water here actually, we just use the water content in ringwoodite to represent our hydrous model. So here we also consider that as water partitioning between Audubon, wazlite, and ringwoodite. So the most prominent feature, okay, we look at those hydrous model is, we can see that, okay, look, if we look at this yellow line here, the yellow line means that water is present in ringwoodite in the octahedral sites. So in this case, if we only add 0.25 weight% of water in ringwoodite, water is present in the octahedral sites of ringwoodite, okay. The influence of water, okay, on the both VP and VS actually is very small. So if we only look at the VS, if the mantle is completely water saturated, okay, that means the ringwoodite contains about more than 1 weight% of water, okay? So this amount of water can only lower the sound velocity of VS, okay, the shear wave velocity, by only 1%. But from the seismology, they observe more than 2%, that is 2 to 7% reduction in the shear wave. So in this case, okay, if water is present in the octahedral sites of the ringwoodite, it's impossible if we try to use the water in transitional to explain the low shear wave velocity anomaly. So how about if water is present in both octahedral and tetrahedral sites of ringwoodite? Okay, so in this case, you can see that. Let's look at the purple line here, okay? The purple line, the solid purple line means less water content, and the dashed purple line means water saturated condition. So in this case, okay, if ringwoodite contains about more than 0.5 weight% of water, okay, in the shear wave, you can see that, yes, it can cause more than 2.2% reduction in the shear wave. But the problem is, at the same time, okay, look at the VP, this dashed purple line here. That means we are going to have a negative velocity jump at a 520 kilometer depth. This was never reported by seismic studies. So we think that maybe it's very difficult to use water to explain the observed low velocity anomaly, okay, at the bottom of the transition zone. Another possibility is, how about the accumulation of the subducted oceanic crust at the bottom of the transition zone? Okay, so we model this again. So we'll also look at this, okay, the bottom, the panel C and panel D are our modeling results, use the Brillouin experimental results together with previous experimental results. The black line here also the paralytic mantle, okay, paralytic velocity mantle, okay, we see. And how about the subducted oceanic crust? The subducted oceanic crust is represented by the red line here. So for both VP and VS, at the bottom of the transition zone, that means that is below 520 kilometer depth. We see that both VP and VS of the subducted oceanic crust are actually slower than the paralytic mantle, especially for the VS. VS of the subducted oceanic crust has been 2% lower than the paralytic mantle. So how about if we change the composition? If we double the iron content, and if we also oxidize the iron, okay, we change the ferrous iron into ferric iron, as Kasiva, they reported in 2019 in Nature Geoscience. They discovered oxidized garnet, methylated garnet from the mantle xenonus. So if this is true, okay, if this happens in the rivers, okay, so we can see that the subducted oceanic crust, the VS, represent by this dark green line here. Actually, this will be 4.5% lower than the Paleolithic mantle. How about if we have the calcium depleted and oxidized methylated garnet? As Xu et al. Reported, they discovered the mantle xenonus contained a very calcium depleted but ferric iron bearing enriched methylated garnet from Eastern China. Okay, this is from the mantle xenonus. So in this case, we can look at this blue line here. We can find that the VS of this calcium depleted but iron oxidized methylated garnet, okay, in the subducted oceanic crust, the VS will be more than 8% lower than the Paleolithic mantle. So let's go back to the seismic observation. The seismic observation, they discover about more than 2%, 2 to 7.4% reduction in the shear wave at the bottom of the transition zone. So that means here we show that, yeah, if water is only present as hydroxyl in mantle minerals, it will be very difficult to explain those velocity anomaly. So another opportunity is maybe the low velocity anomaly at the bottom of the transition zone is caused by the accumulation of the subducted oceanic crust. So this is another example that we use the experimental results obtained from Brillouin scattering that we get at BMD GC cars. We try to understand the formation mechanism of the low velocity layer, okay, at the bottom of the transition zone. So this is about the mineral. Actually, we can also use this technique to get the sound velocity of the fluids. Here I show you one example that our most recent work, this is unpublished, is we measure the sound velocity of this water fluid, water plus 0.5 more volume, more percent of sodium chloride. Okay, this salty water. So here you can see that we also use the external heated diamonds cell. This work is performed at BMD GC cars. We already can go to 1350 Kelvin. Okay, this is a maximum temperature that we can reach now. So we can see that, yeah, we're still working on this project. I just want to share with you these results. You can see those beautiful velocity measurements. We actually get the sound velocity of this supercritical fluid. So this can give us some information about how the water fluid will behave in the Earth's deep interior. So this is about Earth science. We also can use the Brillouin scattering, try to understand the elasticity of the ice. So this one is this example that we actually published this year in GRL, that is about the single crystal elasticity of the salty ice. So we add a little bit of salt into our ice, we can get some very nice single crystal. And from this work, the interesting thing is that we can see that go from an I7. So look at the, I cannot mark. I don't know why. Okay. So anyway, so look at the right panel, panel C and panel D, that is a single crystal. So we can see that when we go from I7 and to the dynamic disordered I7, there is an anomalous drop in the C11 and the C12. And the C44 actually is not affected strongly. It's only weakly affected by this transition from I7 to the dynamic disorder I7. And we also get the single crystal elasticity of this I10 up to 94 GPa. So we also use the Brillouin scattering, and together with the X-ray diffraction at the GC cars, we actually also track the very small volume change when we go from I7 to the dynamic disorder I7, shown by the panel B on your right, top right. So So this is another example that we also use a Brillouin scattering, try to understand the elasticity behavior of the ice. And we know that the ice is the dominant phase in some planets. Okay, so this can also be applied to understand the composition of some planets in the solar system. So using this single crystal elasticity of the solid ice, we also can calculate the anisotropy, the maximum azimuthal anisotropy, that is for the VP, and also the shear wave splitting of this ice. We can see, and we can compare with the lower mantle minerals. The interesting thing is you can see that with increasing pressure, the anisotropy of the single crystal ice actually dramatically increase with pressure. And there is also a Lorimer's behavior when it goes from the I7 to the dynamic disordered I7. There is a slight softening in the shear wave splitting. Okay, so when it go across this transition. So this is one interesting thing. So how about future about the Brillouin scattering? There are some challenging actually in Brillouin scattering experiments. The most challenging thing is when we are working on the mantle minerals, actually the signal is very weak when we go to pressures above 20 GPa. Another very unlucky thing is the P wave of most minerals. Okay, P wave of every mineral will increase with pressure. And a very unlucky thing is the signal is weak and it will gradually overlap with the diamond S wave. Okay, look at this red line here. This is example of the ice. So you can see the VP of the ice gradually get closer and closer to the diamond, and then finally will overlap with diamond. We can never see the VP of this VP anymore. So that means for mantle minerals, actually, when we go above 25 GPa, we cannot get the information of the P wave at all. So this is very unlucky. So in this case, we cannot use Brillouin scattering to resolve the single crystal elasticity for most of the mantle minerals above 25 GPa. The good thing of the ice is the signal of the ice is very strong. So that's the reason when the VP of the ice is faster than the diamond VS, we can see this VP peak again, showing by the panel G on your left. But for most of the mantle minerals, we cannot do it at all because it's very weak. So in this case, how about how to overcome this problem? I think after Lin at UT Austin show a very good example. Okay, we can combine the stimulate light scattering with Brillouin scattering. They have used this, combine those two techniques to solve the single crystal elasticity up to 70 GPa. Very beautiful work. And another thing, I really expect that maybe we can do this at JC Cars BMD in the future, that we can add laser heating. Okay, combine the laser heating with the Brillouin scattering in the future, because I have been working on Brillouin scattering for so many years, especially use the externally heated diamond cell. But honestly speaking, it's very challenging to go higher temperature above 1000 Kelvin. But we know that although I have reached about 1700 Kelvin, it's still lower than the mantle temperature. So maybe in the future, like Zhang et al., they did in New Mexico University, okay, maybe in the future at BMD, we can see the combine, we can see that we can perform the laser heating experiments together with the Brillouin scattering. So that is what I have today. Thank you so much.
So for the audience, we have time for 1 or 2 quick questions. Please raise your hand. I think the first, Alex, please unmute yourself.
Yes, this is a very nice talk. You know, I really enjoyed it. Could you please tell me, how did you make single crystals of I7, I10, and salted water, also salted crystals like that?
Okay. So this is actually very interesting. Okay, so we add salt inside. So we gradually increase pressure and try to increase and release pressure and by several times. and we check it with the X-ray diffraction, and we can grow the single crystal. So another way that to grow the single crystal of ice, beautiful single, even better single crystal ice is you can you can start with ammonia hydride, ammonia. So when you increase pressure, okay, you add ammonia into your diamond cell, you slowly increase your pressure, you are going to dehydrate as ammonia. So you are going to separate your ammonia into ammonia half hydride and single crystal ice. That single crystal ice may contain a little bit of nitrogen inside, but that single crystal has the quality of that single crystal is even better than this salty ice. So there's no magic, just a slowly increase pressure that we can do this. Yeah, this is very interesting. Yeah, I think it's much easier to grow good single crystal ice from if you add a little bit of salt inside instead of grow it from the pure ice.
So I didn't get it. What you said, add what?
Add a little bit of sodium chloride inside.
Sodium
This
chloride.
can help you. Yeah, this can help you a lot, I would say.
Okay, thank you.
Yeah, so we have another question from Jin Zhang.
Really excellent talk. I really enjoyed it. It's just so great. I have a small question related to how to calculate the water effect on reumudite, because I recently we ran across another paper from the Brillouin group by Scholz et al. 2018 EPLSL paper on the hydrous reumudite. It almost has exactly the same composition as your 2012 paper, but these two results are just so different. Their velocities are about 2 or 3% higher than your velocities. So I'm just wondering, what do you have any explanations for this and what's going on basically?
Yeah, we have discussed this actually in our paper. Okay, yeah, the time is limited. I didn't discuss this. I think the major thing is the water incorporation mechanism. So when you, as I said, that when your water or hydrogen is present in the octahedral size, okay, the influence of water on the sound velocity of reumudite is much, much less. Yeah, I think this mechanism the influence has been discussed in the published paper in the EPSL, I think. Yeah.
Okay.
Though actually, yeah, because this is already an old paper in 2012. At that time, we didn't check the water incorporation mechanism of our reumudite. But nowadays, people discover that, yeah, different water incorporation mechanism can cause different influence on the sound velocity of reumudite.
Okay,
so in the real Earth, which one? I'm sorry.
This discussion. So, but for the interest of time, so we should move on to the next speaker. So you can continue to discuss it in chat.